Hey, this is Leach with Simpson Math, and today we're going to be talking about graphing polynomials. Last time we looked at the end behavior of polynomials and made some very rough sketches of these polynomials using the leading coefficient and the degree of the polynomial, and also figured out how many terms we'd expect, how many roots we'd expect, and made some very rough sketches. We also, kind of for fun, found the x and y intercepts in preparation for today's lecture. So we're going to be making some more precise graphs than last time. They're still going to generally be rough, but making some more precise graphs. And then talking about a new term called multiplicity, which uses the number of times we see multiple of the same roots and how that impacts our graph. So let's get started. It says use what we learned last lecture to graph f of x equals 2x cubed minus 3x squared minus 8x minus 12. Now, what we learned last lecture was about end behavior. So we first start by looking at the leading coefficient, which is 2. That's a positive number, so I know that it is going to be rising to the right. Because 2 is positive, it's going to rise to the right. If it was negative, it would fall to the right. All right, next we're going to look at the degree of the polynomial, which is 3. Since this polynomial is in correct order, in descending order, this leading term has the degree of the leading term is that degree of the total polynomial. That 3 tells us that we expect 3 roots, and that we expect one less than that number of turns, so 2 total turns. But more importantly, since this is odd, that means that when we go to the left, it's going to be opposite of what's happening to the right. So that means we are going to be falling to the left. And so here we have all these things. The degree of the polynomial is 3. It's going to fall to the left. We have 3 roots, so that means we expect 3 x-intercepts, and we expect 2 turns. And then as a rough sketch, it looks like this. And so that's what we talked about last time. For fun, I said we could move on and find the x and y intercepts. This time it's going to be required to find those. So first, our y-intercept is simply, as we saw, it's just going to be that value, 0, negative 12. Because if I plug zeros into all of my x values, I'll be left with just, that should be a negative 12. Let me correct that. All right, there we go. I fixed it. It now says 0, negative 12. And it is negative because our constant is a negative 12. So make sure that those signs do need to agree. Next, we need to find our x-intercepts. To do that, we make the y value, the function value be 0, and then solve for x. And we can do this by factoring by grouping. So I can group together the first 2 terms, and we end up factoring out an x squared. And then I can group up the second 2 terms, and we factor out a negative 4. And then we notice that we notice that it's 2x plus 3 in both, and so we factor out a 2x plus 3 from both, and we end up with 2x plus 3 times x squared minus 4. But notice that x squared minus 4 is a difference of 2 squares, so we can keep going and factor that as well. So when we factor the x squared minus 4, we end up with an x plus 2x minus 2 for that factoring. So overall, we have these 3 factors, 2x plus 3, x plus 2, x minus 2. We can set each of those equal to 0. So y equals 0 when x is negative 3/2, when x is negative 2, and when x is 2. So we're going to use our x-intercepts, our y-intercepts, and our information about end behavior to sketch this graph. All right, so here's this coordinate grid that I have drawn up already. I've already left myself a few notes. So I have it here in this top right corner. I'm saying that I am going to be rising to the right. And then in the bottom left corner, I have the note that I'm going to be falling to the left. And I'm going ahead and put a dot at my, I'm missing one. At negative 1.5. You can take them.
I just saw Hank over there.
Yeah, the jalapeno. He's
She's texting you
no.
Come on.
All right, so here's a coordinate grid, and I've gone ahead and left myself a few notes from the stuff that we previously done. So we have our function rising to the right, so I just left a little note saying that I'm going up to the right, rising to the right. Bottom left corner, I now see that I'm going to be falling to the left, so I know that this function is going to start here, do something, and then end up high. And I have my three x-intercepts labeled with a dot there, so I know where they're going to be touching or crossing the x-axis. And then I've also labeled my y-intercept. So this tells me that somehow my function starts at the bottom. It's going to have to cross through the x-axis, then cross through it again, then at some point go through the y-axis, and then cross through the x-axis, and then go up. So I know that that's my general shape of my function here. I just need to make it be nice and smooth and connected. One important point about this particular function in many of these polynomials is look at my scale. So on my x-axis, I have every 4 squares of my grid is a unit, but on my y-axis, I have every 2 squares is actually 3 units. So that would actually mean that it'd be about this much for 1 unit, 2nd unit, 3rd unit. Because polynomial functions tend to have, they get really tall. So because they get really tall, you might need to have your y-axis be a little bit skinnier, be a little bit more, have smaller jumps than your x-axis. But whatever you do, make sure along the x-axis it's consistent, and along the y-axis it's consistent. So what I need to do now is just to smoothly draw my function. So I start at the bottom, pass through that -2, pass back through the 3/2, come down, go through the -12, and up through the 2, and then arrows on either end. Something about like that. Just a note, this is what we can consider a detailed sketch. I'm not actually finding any other points. This is really it. In order to find where the graph actually turns around here or turns around here, that's going to require calculus. And this is not a calculus course, so we're not going to be worrying about that today. If you wanted to be a little bit more precise, you could figure out where the graph is at 1. So plug 1 into the function and get an estimate, and then figure out more precisely where that graph is there. So if you want a few more points, be my guest, just plug in some x's and plot those. But at minimum, this is what I need. All right, let's move on to a second example. All right, so this time we have g of x is x squared plus 6x plus 9. Let's do the things that we did last time with the end behavior. So what's our leading coefficient? Well, it's just 1, which is positive, so we're rising to the right. Then our degree of the polynomial is 2, so that means that it is even, so it will also rise to the left because it's the same end behavior as the right. We have 2 roots, so that means we expect 2 x-intercepts, and we expect just 1 term. I can find y-intercept by just plugging in zeros or just grabbing that constant. And so I know that my y-intercept is at 0, 9. But in order to find the roots, I'm going to have to factor. So I do AC method, and I get 1 times 9 is 9. What multiplies to be 9 and adds to be 6? Well, that's 3 and 3. So we can go ahead and factor this. And so it's x plus 3, and we can put that together to be x plus 3 squared. I don't have to do both of these, but just to show you that if I set both x plus 3's equal to 0, we get the same thing. This is what's called a double root. We still have 2 roots. They're just on top of each other. So we have really just 1 x-intercept, but we still technically have 2 roots. So our 1 x-intercept is at negative 3 comma 0. All right, so let's graph this. Well, you should notice that we now have g of x equal to x plus 3 quantity squared, x plus 3, all of that squared. Well, if I would have asked you to do this a few weeks ago, you should have had no problem doing this. This is just a parabola that's been moved 3 units to the left. Hopefully that's what you were saying to me. 3 units to the left. So I can graph this by just taking a parabola and moving it 3 units to the left. And it looks like this. So you see we have a parabola that's been moved 3 units to the left. We have an x-intercept at negative 3 comma 0, like we knew that we would. We also had our y-intercept at 0, 9. We were rising to the right and rising to the left. All these things agree, but I was also able just to graph it using my transformations. Left 3, and then 0, 0, 1, 1, 2, 4, 3, 9, and it's symmetric, so I could get the other points. Now, when it comes to parabolas, actually at the end of this lecture, or it will be the next video, I'm going to go into some more detail about what I would like to see when it comes to a parabola. It's not just the graph. There's going to be some other things that go along with that. So check that video out to see what other questions I'll be asking when it comes to a parabola. But let's talk a little bit more about what just happened. So we had a double root. And so I want you to notice what the relationship with our x-intercept and the parabola, or just in general this polynomial. This is what's at play is what's called multiplicity. So multiplicity, it's the number of times a certain factor occurs, aka the exponent. But a pattern does arise from this count. So if I have an odd multiplicity, meaning there's an odd number of times that I have each unique factor, then what's going to happen is that the parabola, the function, is going to cross the x-axis at that real root. And then, secondly, if I have an even multiplicity, meaning the exponent on that factor is even, then it's going to touch and turn away from the x-axis. So it's going to touch the x-axis and then just turn away. Larger numbers have a little bit more extreme crossings or touches and turns, like we'll see in a little bit of the notes. All right. So let's just go back to the last 2 examples that we did. Our f of x was this, and when we factored it, became this. And we noticed that each of our factors just occurs once. And there's an implied exponent of 1. Remember, there's always exponents of 1s. If you don't see any exponents, we have an understood 1 to be there. So there's an understood 1 in each of these locations. And so that means they have a multiplicity of 1, which is odd. So at 2, at negative 1/2, and at positive 2, it's going to just cross through the x-axis. But this g function, my one unique factor is x plus 3, and I have 2 of them. So I could write it as x plus 3 squared. So x plus 3 has a multiplicity of 2. So that means whenever I graph this, it's going to touch the x-axis at that negative 3 and then turn around. Some people think of it as like bouncing. It like bounces off the x-axis. I just refer to it as touching and turning. All right, so let's take a look at another function. And then let's actually then deal with this multiplicity. So we have this h of x function. Notice it is to the 4th power. You don't know how to factor things to the 4th power. And actually in a few lectures from now, we'll actually cover how to factor this. So you're getting this for free today. So it does factor into 3x minus 1, x minus 3 squared, and x plus 2. So first, before we deal with this multiplicity stuff, let's go through our end behavior business. So it has a leading coefficient of 3, so that means that it is going to rise to the right, and it has an even degree of the polynomial from this 4, so then we know that it's also going to rise to the left, and we expect 4 x-intercepts. We know there's 4 roots, and then we expect 3 turns. We can also get our y-intercept from this negative 18 at 0, negative 18. All right, so now let's talk about our roots, or the multiplicity of those. So notice from our exponents, what's the exponent on 3x minus 1? Well, there's just an understood implied 1 there. What's the exponent on x minus 3? Well, there's that 2. And what's the exponent on x plus 2? Again, there's an understood 1 right here. So that means that that means that 3x minus 1 and x plus 2 have multiplicity of 1, meaning at these roots they will cross, and x minus 3 has a multiplicity of 2, meaning at this root it's going to touch and turn. So when I solve each of these factors for x and to find the roots, this factor gives me a root of 1/3, x minus 3 gives me a factor of 3, and x plus 2 gives me a factor of -2. I misspoke. X plus 3 gives me a root of -2. And as I said earlier, at x equals 1/3, because it is odd multiplicity, it's going to cross. Along with at x equals -2, it also has odd multiplicity, so it won't just simply cross. And then when x is 3, it has even multiplicity, so it's going to touch and turn. So let's graph this. All right, so when it comes to graphing things with multiplicity, I need to be aware about what's happening at each of the x-intercepts. So I know that when it's at x is 1/3 and when x is -2, it's going to cross somehow. And I know that whenever I'm at x is 3, it's either going to touch and turn like this or touch and turn like that. Well, it's kind of like a little bit of a puzzle. I need to piece some of this together. So if I'm starting on the left, up high, and then I'm coming through, I know I'm going to have to cross at -2, and then actually go through my y-intercept, and then cross back up through this 1/3, and then somehow touch and turn at this 3, and then in high. Well, that's sort of kind of a very rough sketch of what's happening with this function. All right, so now that I've envisioned this, or maybe even lightly done it on paper, I'm going to optionally also show you another trick, is to leave little notes with myself. So I know at 2, it's going to cross, -2, it's going to cross. At 1/3, it's going to cross right there. And at 3, it's going to touch and turn. So I'm just making very, very, very light notes to myself so that way I can graph this a little bit easily. All right, so let's swoop this. Now, I do know that I'm going to have to go down quite a bit because on its way up, it's going to go through this -18 and then through that 1/3. So I'm going to have this be rather steep and then swoop up. So let's do that. So it's rather steep and it comes down through the -2, somewhere turns around, and then comes back up, crosses through the -18, crosses through the -1, somewhere it's going to have to start turning around, and then touch and turn at the 3, and then go up. And there we have it. And do note that I have leftover already, but I have my h of x already there, so that way my function is labeled. So I made those little notes to myself, and you honestly can't see them right here, so I'm not going to worry about erasing them, but that just helped me make sure that I found my multiplicity. So again, let me review our multiplicity now that it's graphed. So notice when x is 1/3, it crosses. When x is -2, it crosses. And then when x is 3, it touches and turns. So that's our multiplicity. I have this example I'm just going to go through super quick, just so you can see another example. All right, so first up, we have to make sure to put it in the correct order because it wasn't already. It needs to be in descending order. Then I'm going to think about my end behavior. My leading coefficient is negative, so I'm going to fall to the right. My degree of the polynomial is 3, so on the opposite side, on the left, I'm going to be on the opposite direction, so it's going to rise left. I have 3 roots, so that means I expect 3 x-intercepts, and then I expect 2 turns, and my y-intercept is 0, 0. My y-intercept is 0, 0 because there's an implied plus 0 right here. And since my y-intercept is 0, 0, that's also one of our x-intercepts. All right, to get the other x-intercepts, I'll need to factor. So we first factor out our GCF. Our GCF is a -x, so I can factor that out. And left-hand side is a difference of 2 squares. So we can then say that's 2x plus 5 times 2x minus 5. All right, so my roots are x equals 0, x equals negative 5 halves, and x is 5 halves. And the x-intercepts will then be the points from that 0, 0, negative 5 halves 0, and 5 halves 0. When we take a look at the multiplicity, each factor only occurs once, so they will all cross, and they're all real. So when we graph it, it then looks like this. So notice at 0, negative 5 halves, and 5 halves, they all cross, and we are falling to the right and rising to the left, and our y-intercept was also 0, 0, so that's where we got this function. All right. The next set of examples, I'm not going to walk through specifically. I just want us to focus on the multiplicity. So here is a cubic function that later, I'll be showing you later, as in like 2 lectures from now, I'll be showing you how you can factor and get x minus 6 cubed. But it is x minus 6 cubed. That is a multiplicity of 3. And so you could have graphed this just a few weeks ago when we were talking about transformations of functions. This is just a cubic function that's been shifted 6 units to the right. And notice it is crossing through the x-axis at 6. But it does have what I call, has a little bit of a wiggle. It wiggles as it goes through the 6, because I said a second ago when I was introducing multiplicity, when it's not just a 1 or a 2, but it's a higher power, they do a little bit, their behavior is a little bit more extreme. So when it's this cubed or a 5th or a 7th, it does a little bit of a wiggle. And the higher that it is, it's actually just sort of kind of more extreme, the closer to the x-axis that it occurs. All right. I'm not going to graph the y-intercept because it's at 0, negative 216. So you get the point. Way down there, it'll be crossing. All right. So all I've done is now I've just tacked on an extra x. So if you compare these two functions, they're basically the same thing. I've just multiplied an extra x across in b of x. So now I could factor out that x and then end up with the same factors, x minus 6 cubed. So what's happening is I have a multiplicity of 3 at the root x is 6, and then a multiplicity of 1 when x is 0. So it's going to cross through at 0, and we'll also cross at 6, but we'll do that bit of a wiggle. And it starts high and ends high, so it comes through like this. Now I have dots in here because it goes way down there. All right, next. All right, all I've done again is multiply by another x. So now it is this 5th power, and I could factor out an x squared and then be left with that same x minus 6 cubed. So again, I have my cubed and it has that wiggle. But this time my x squared, it is a multiplicity of 2. So it's going to touch and turn at 0. And it rises to the right and falls to the left. So it starts low, comes up, touches and turns, goes down somewhere down, way down there, it'll turn around, and then does its wiggle through 6. One more like this, and it's d of x. Here I've multiplied the original a of x by x cubed. So when I factor out that x cubed, I have two things with multiplicity of 3. So at 0, it crosses again, but now it does that wiggle, and it wiggles on both sides at 0 and at 6. And it's interesting how the wiggles are sort of kind of mirror images of each other. All right, so I hope that helps you see just the subtle differences with the different multiplicities. I have two more quick examples. I'm not going to actually do them per se. I'm just going to show them and talk about them. All right, so we have this one. I have a 5th power. This can be factored. You can factor out this x squared, and then you'll just be left with a cubic that you can then factor by grouping. And so we end up with this x squared, which has even multiplicity. So at 0, notice it touches and turns, but all the others have odd multiplicity, and so they're across through at those locations. So we have this 5th power that rises to the right, falls to the left, and it crosses through like this. Touches and turns, crosses through, crosses through. And so that is our N of x function. And then just to show you one that you should have already done from your homework. Number 2 on your homework was 2x to the 4th plus 2x cubed minus 4x squared. When you did all that factoring, notice you ended up with a x squared, x plus 2, and x minus 1. Well, this x squared is a multiplicity of 2, so it behaves like this. We have this multiplicity of 2 at that 0, but at 1 and negative 2 it crosses, so it behaves like this. All right? So that's graphing polynomials. Our next video is just going to be a little bit more specific look at what I expect from you when we graph quadratics, because quadratics are a more specific and special polynomial. I'm going to be asking for a few specific things, and so we'll see that in that next video. Hope this helped, and we'll see you next time.